Hi, everyone. I'm really glad to be here. This is actually my first proposal I've made for a Postgres conference. So I really am honored that the talk was selected and appreciate the opportunity to share this information with you. And I'm really excited to be back in New York. I haven't been here for a few years and got to pick up some bagels and pizza while I'm here. So this talk, by the way, is available right now online on Speaker Deck to view, and you can download the PDF as well. It's at bit.ly/pg-fitter-happier. And I'll put that link at the end as well. So there's a bunch of information in here and a lot of links. So if you don't want to furiously type or write, you can just download this deck later. If you didn't already pick up on this, thanks to Radiohead's Fitter Happier song from 1997 for the inspiration for my talk title. A little bit about me. I'm a staff software engineer at Fountain. I've recently joined Fountain. You can find me online at andyatkinson.com, or I'm on Twitter as well, @atky. I've recently joined Fountain, and in case you're not familiar with it, we're a startup company. We've recently raised a Series C round. This talk today is not about Fountain. It's actually about my previous employer. But I did want to shout out Fountain and mention that we're hiring database administrators, infrastructure engineers, software engineers, all sorts of roles right now. If you're interested in that, I do have a bunch of swag and t-shirts and stickers and pens, so hit me up afterwards. I love to talk with you about Fountain or Postgres, and the hiring link is here. So this ends the advertisement portion. Okay, so the inspiration for this talk. I'm mostly an application developer. I've been doing it for about 15 years, and I was working for a company where our platform experienced a huge usage increase due to the COVID-19 pandemic. So the product is an education product. It's a video discussion platform, and as the world sort of shifted to distance-based learning, the product became extremely popular amongst K through 12 educators to try out to communicate with their students. So we saw at our lowest points around 40,000 requests per minute in our web application, all the way up to around 400,000 requests per minute. So that put a serious load on our application servers and our database server. And we were a small team, just 5 engineers when I joined on the back end, and we had no database administrator. So there was a lot of opportunities to really take kind of a vanilla Postgres installation and learn to utilize it better. So over half a year or so, we worked on several small, medium, large-sized projects, and that's really what inspired me to put this together. So this talk is intended sort of as a case study, sort of a practical talk, and I hope some of this might be useful for you all in operating your Postgres installations as well. So I wanted to share our challenges and findings and some results that we had, and then connect our challenges with common scaling and challenges. Let me just start my timer here. I forgot to do that. And our backend was powered by Ruby on Rails and Postgres 10, and we were using AWS's RDS offering. And our architecture was pretty simple. It was really just a single primary Postgres with, we did use async replication, but really just one database that eventually, we kind of used more as a write database, which I'll get into. And so the talk today is structured in 4 categories because there's a bunch of information here, and hopefully it's helpful to put the information into context, kind of across administration and query performance tuning and different categories. So we're going to cover connections or database connections, space or space utilization or space reduction, performance, which is query performance, could be auto vacuum performance, and then different types of errors that are common in operating Postgres. So first we'll jump in the order of these categories is kind of random, but first we'll jump into connections. So we learned that we experienced and learned about some database connections problems as our web app and database activity load increased and we reached connection limits, our performance degraded. Our web app servers, eventually we did exhaust all of the available connections, and we would see errors that were kind of roughly this, is the server running? But basically there were no connections available. And this was very bad because that meant we could not add additional app servers that would require more database connections or background processes that would require database connections to really serve that load that we had. And I learned some things about connections with Postgres. So the architecture is such that each new client connection, Postgres will fork a process for that client connection. And in that sense, connections are costly, and they are limited, and they're correlated with the available resources of the database server. And connections can be in several different states. These are some of the states. They could be actively performing a transaction. They could be idle. They could be in a transaction, but idle in that transaction. So there's different classes of problems associated with these different states as well. Too many idle connections can be a problem. Connections in a transaction that are idle but are old, that can also be a problem. So these are interesting things to monitor. There's a lot of different monitoring tools. This was one I just selected to show a visualization of this. So this is PG-, just calling out the bottom here. It's showing transactions that are open but have been open for too long. What I would do with this information then is go and try to figure out where these queries are coming from in the application and see if there's any remediations we can do. We'll talk about some more safeguards later too. So commonly folks will go for connection pooling at the infrastructure level. We did have connection pooling at the application level with Ruby on Rails. Active Record has a connection pooler. I imagine there are similar things for Python and other frameworks, such as Django or something like that. So some common infrastructure connection poolers are PG Bouncer, which can be monitored by PG- as well, PG Pool 2, and Amazon has something called RDS Proxy. So here's a look at PG Bouncer running, monitored by PG-. Just to, again, show a visual, we can see server connections and client connections. So client connections are going to be the connections between the app and the pooler, and server connections are going to be between the pooler and the database. And so, you're able to then monitor your application connections. What are the benefits of a connection pooler? Connection pooling, primarily it's two big things. It's being able to use, especially for web applications with a lot of short in the sense of low execution time and concurrent transactions, being able to really scale those up beyond the limits of the physical database connections. And then there's also a performance benefit in more efficiently utilizing those connections amongst many transactions. And let's see, so yeah, basically those are the two things, right? So we can safely add more app servers, and this is common in an auto-scaling scenario, right? If you have an application structure that might add more servers to meet additional load, if you have kind of seasonal, or let's say you have an e-commerce website with a lot of load around Black Friday or something like that, you might want to add more servers to meet that load. And right, and then the more efficient reuse of the connections. So for our team, we selected RDS Proxy. We were already running on RDS, and we were a small team, as I mentioned before, and that gave us the opportunity to utilize the connection pooling benefits without having to maintain additional infrastructure. And we did really see what was advertised on the box. We no longer ran out of connections, and we actually saw improved performance. We didn't see the degraded performance, so it was really a big win for our team. And in our most urgent, critical scaling period, it was one of the biggest wins. So that's kind of what I have for database connections. So let's move into space, or disk space usage. As we were scaling up, we observed a number of things about our disk usage. So we noticed that tables and indexes had a very high bloat percentage, or an estimated percentage. We noticed that, or we were aware of, without like a dedicated database administrator or a lot of PG-focused expertise on the team, no one had done any bloat reductions before. And we had a lot of non-optimized indexes. Over time, application developers introduced indexes that either were not optimal or just weren't used at all, which I'll talk about a little bit. So Postgres was a little bit bloated and a little bit unhealthy, but we could fix it up. So there's some things to learn about space reduction for indexes. bloated indexes can be rebuilt entirely, and when they're rebuilt, they will no longer have the bloat. So you can eliminate that bloat. That bloat is intended to be removed by, well, let me stop there. But that's a way to quickly remove the bloat. Indexes can also be reduced in size if they over-index fields that are not actually necessary. You can reduce the fields. We'll also talk about reducing the rows that an index includes as well. And then, one of the biggest wins, even without knowing a lot about the application, is to take advantage of removing unused indexes or other unnecessary indexes to reclaim space and make that available. So we used a tool called PGHero, which is somewhat common in the Ruby on Rails community for Postgres as a performance dashboard. And it can be run separately on a Docker image as well, outside of Rails. So I have a local Rails app that is kind of like an Uber or a Lyft with some trips and riders and drivers and trip requests to just sort of test things out. So that's what we're seeing here. And this is a very small database, just 10 megabytes. But the intention of this slide was to just show how PGHero shows the tables and the indexes or the relations. And then we'll get into this a little bit more later, but any indexes that are unused are also labeled there too. It might be hard to see, but there's unused labels on some of those indexes. So right away, that's an opportunity to remove those. So I'm calling them non-optimized indexes, but there's additional categories. So amongst our 75 tables in our main monolith app, we actually had over 100 that were unused, which for me was pretty surprising. I was relatively new to the organization, and it was a pretty big proportion of the total number of indexes. A lot of them were unused, and that might be fairly common. It's something to look into in your application if you're not already looking at that. And then some of the indexes had very high bloat percentage. Again, this is an estimate, but some were estimated at more than 80% bloat content. So those invisible rows were not removed properly. And that meant if we rebuilt those indexes, they could be potentially 20% of their original size. And some of those indexes were quite large. Our total database size was 2.5 terabytes before starting. But some of these indexes were over 100 gigabytes. So that was a big opportunity to make a significant dent in the space usage. So we decided to rebuild indexes. We selected, on PG10, we selected PG Repack, and I personally ran through about 30 of these. We worked backwards from the most bloated indexes to the least bloated. Very large indexes I would recommend trying to rebuild at an off-peak time. There can be significant read and write I/O associated with rebuilding the indexes, so that's something to be aware of. And if you're on Postgres 12 or newer, I would recommend reindex concurrently, which is built in, which will allow you to achieve a similar end result. And so yeah, we were able to rebuild 30 indexes one by one and reclaim 230 gigabytes of space. Little matrix reference for you. Okay, so we also removed unused indexes. And again, the context of this section of slides is talking about space reduction. So we found Postgres tracks index scans internally. So we were able to then find indexes with no scans and confirm there were no usages across the app or cron jobs or that sort of thing. And as an extra due diligence step. And then in Rails, we would create a migration to drop the index. So over a period of months, doing this by one at a time or a small batch at a time, we removed those 100 that I mentioned that were unused, which freed up 300 gigabytes of space. And then a bigger effort, this is a more complex project, but another engineer had noticed that we had these collections of tables that were really metrics oriented. So they would track data about some other primary piece of data. And they would track, for example, as a video discussion platform, if a user viewed a video, we would drop a record for that. We would insert a record. So the tables were heavily written to. They had a much higher proportion of writes compared with the primary object they referenced. And they were basically insert only. they typically were not queried in the application apart from a couple of spots. So what we thought was that actually contributed to a big portion of our write workload, and we could actually relocate those tables to their own metrics kind of database, which is what we did. That data, again, was across 6 tables. They all had a similar structure, and they represented about 700 gigabytes of space. So our process, we didn't want to take any downtime to be able to do this. So our process was, RDS makes it pretty easy to, given enough replication slots available, add another replica. So we added a replica with the intention of converting it to a primary database. Prior to doing that, what we did was we looked at the queries that were, any queries that were utilizing this data, and there were some joins and some statements that referenced these tables that we intended to move. So first what we needed to do was make code changes to stop that, because of course we can't join across databases, and even doing like a aggregate or something, some sort of statement that references those tables was going to be problematic after they were moved to a new database. So we did make some code changes there in order to, and typically that looked like taking a single query that was a little more optimal and breaking it into a couple of queries. But if they ran slowly and in the background and stuff, it was worth the trade-off. And then, so yeah, we had created the replica, right? And then we intended to move that to be a writer database. But initially, we just were querying from that. So we could deploy, we had a couple of deploys to make this process work. Initially, we deployed to move the read queries. And then we did kind of a double write situation, writing to the current database and the new database briefly, although those writes to the new database would fail as it was a read-only. But we could handle those failures. And then we would do the promotion, which we were able to test in pre-production environments first. But on RDS, the promotion process of promoting a replica was fast. So once that was in place, then we were writing to both locations. And then we were good to go, because then we could stop the writes on the old location and remove all of those tables from that primary DB. So this is definitely one of my favorite memes. If you've never seen it, I'm always looking for ways to use it. This is not my best meme generation, but it's all I could come up with for this slide. So Grandma's saying, in my day, databases were half the size. And sure, Grandma, let's get you back to your room. But so we started out with 2.5 terabytes. And we didn't really intend to just reduce space, but I thought it was interesting to pull these things together as kind of a category. So we, through a process of relocating the tables for 700 gigabytes, removing the unused indexes for 300, removing index bloat for 200, we actually reduced the database to half the original size. Again, we didn't really set out to do that, but having a smaller database on the same infrastructure theoretically would give us some more headroom and allow more memory to be utilized efficiently and that sort of thing. So that was space and space reduction. Now I'm going to jump into performance. So we had, as I mentioned, our biggest challenge really was usage increase of the app, which is a good thing. We were excited that the app is a valuable app for education setting, and we were excited that it was being used and trialed, but it also made the job for the engineers more challenging to meet that workload. And we also noticed secondary things in trying to put out fires with production incidents and stuff that were interesting and required a little bit more Postgres learning and investigation, such as just really the whole topic of auto vacuum. So auto vacuum was not running at all for some tables. It was running for a very long time, like multiple days. And of course, we had slow queries. That's going to be quite common at a lot of organizations. And oh shoot, I'm getting that squeaking. And then we had these non-optimized indexes, which I'll break down further. So the biggest immediate change being an elastic database offering, we were able to scale up, and fortunately, we did have the budget to make this workable, but we scaled up to a very large instance class, running almost 100 virtual CPUs and almost 800 gigabytes of memory on the primary Postgres. So that gave us On RDS, they'll do some calculated parameter tuning, so that gave us 25% of that system memory, or that memory allocation available for shared buffers, for example. We also were exceeding the read and write I/O that was provided at our price point. So we did purchase additional provisioned I/O to allow us to not run into those limitations. So auto vacuum tuning is something that we did get into as well. The purpose is to make auto vacuum, it was intending to remove dead rows for future inserts and updates. The purpose was to really make that quicker and more effective. And then the broader goal there was to reduce the excessive disk space growth by having a more packed or a less fragmented storage of new rows as they're introduced. And then we also wanted to ensure the statistics about the data that are collected by Analyze when auto vacuum runs. We wanted that to be happening as quickly as possible as well, so that the query execution planner had the most up-to-date data about the data in the tables. And then reduce our auto vacuum runtimes, as a background process. It's intended to not interrupt the production workload, but of course we would prefer to not have it running for days. So again, PG Hero has a maintenance tab where it shows the tables and when they were last vacuumed or analyzed. And this is information you can query using the catalog tables in Postgres as well. I liked this advice for auto vacuum, or guidance for auto vacuum tuning, was to consider it in relation or in proportion to your update and delete workload. And in our application, those views tables that I was mentioning before, where we tracked user behavior, we would often do kind of count queries on those, right? Like 10 users viewed this thing, 20 users viewed this thing. And then we would update that primary row with that aggregate count, because that was a spot where we would show that in the application. So all of those updates, as new rows were coming in, we're updating rows, which, as we know in Postgres, will create a dead tuple to be cleaned up by auto vacuum. So we did have a very high proportion of the updates to the inserts, and we could see that by looking at, in RDS, they have a performance insights tool where you can see your top SQL statements, and you could pop in there at any time and see a lot of updates. And so I would recommend checking out your statement workload and getting a sense for that. If you do have a lot of updates, auto vacuum is probably something to consider scaling up. So we lowered the scale factor, which was the point where auto vacuum would kick in, and we decided to go for like a value that made sense for very large tables. And then we also, the two primary parameters that we did change were the cost limit. So cost limit, when that's reached, the vacuum worker will cancel itself, put itself to sleep, and then start again later. So by increasing that from 200 to 2,000, by raising the cost limit, vacuum would run longer, the process for that table. And we also then decreased the cost delay from 20 milliseconds to 2 milliseconds to decrease the period of time where vacuum was not running. So the combination of these settings was intended to basically give vacuum more resources to work with and to run more aggressively for our workload. Maintenance work memory is interesting as well, but it was sized by RDS and we kept that. And then max workers is something to be aware of as well. If you do have a partitioned table, you can actually have multiple processes at once working on different partitions. We did not have any partitioned tables. So I learned some things about query performance. Query load can be categorized as write or read. Slow queries contribute to system load. Super slow queries are really long-running reads, such as an analytics workflow or an ETL workflow, even on a replica, can actually affect the primary. So I'm not going to get into that too much in this talk, but we did end up moving away from using a replica for our ETL processes to having a disconnected database that we would query from that was refreshed periodically. And then bloat can affect query performance as well. Also love this meme. It's a really good one. So we made the decision to not automatically send queries that could otherwise run on a read-only replica to the read replica because typically it's not that simple. There could be new errors that then crop up if users are expecting to see something that was just inserted and then we query on the replica and it's not yet replicated. That can introduce confusion for users. So we did it more selectively, but the inverse, the corollary to that then is that because it was a manual process. So we essentially tried to drive as much query and read workload as we could to the replica. And we also, of course, I shouldn't say of course, we also did have a high proportion of reads, which my understanding is this is pretty common in web applications, is you could have 5 to 1 or even 10 to 1 or more reads to writes, right? So if you have a lot of reads, being able to shift that workload to a replica or even multiple replicas and then distribute that load is a big win in terms of lessening the workload on the primary write-oriented database, handling those inserts, updates, and deletes. Yes, so we kind of had a process or a pattern that emerged from that, in that we would, doing a time check here, we would typically try to drive this. Typically it wasn't worth our while to just randomly choose queries and move them to the replica. We would try to drive it through our application performance monitoring tool. We used New Relic, or from PG Hero identifying slow queries via PG stat statements, query statistics. We would typically start there, and then we would try to optimize a query, but if it made sense to run the query on the replica, that was also beneficial to the overall system, and we would probably do both of those things at the same time. So yeah, we would determine if the query is read-only, and then we would wrap that in some code that would make a connection to the replica instead of the primary. And then some other tips and techniques that some libraries will use is to, in the event that the item's not found, you're querying on a replica, it's not yet replicated, you can fall back to the primary in that case. Or you can also, another technique is to periodically monitor the replication lag. In the unlikely situation where it gets very high, if you periodically check that and cache that and it is high, you can fall back to the primary in that case. So we learned about some ways that bloat affects query performance as well. Very high bloat can contribute to poor or inaccurate query plans. Since Postgres is selecting a query execution plan at runtime, there are some, I think, less common but possible cases where high bloat can change the query plan in a negative way. Bloat does cause unnecessary scans through pages of data, and bloat can slow down index-only scans, which we'll talk more about. This is more on the altering the database structure side, but we did use a tool called Strong Migrations, and there's other ones. And they essentially tried to codify some common patterns for dangerous operations on databases that are large. Anytime you really alter the database significantly on a large database. And Postgres has made improvements in this area. But on Postgres 10, for example, adding a column with a default value at the same time is considered a dangerous migration. So we would typically try to either catch those through some automated tooling or a code review process. Okay, so we want to fix performance of our slow queries, so we should just index every field, right? Just take all the fields, add it in. Yeah, no, don't do that. Okay, so indexes are, extremely useful and even required sometimes for reducing a query that would otherwise take an unreasonable amount of time. So improving that read execution time, or the execution time of the query. However, there is a cost to them. And they do affect, the biggest cost for us, trying to optimize our write-oriented workload. If you remember, we tried to shift more of the reads to the replica. So that sort of made our primary database more of the write-oriented database, right? So then it was like, well, how do we juice up the rate that we can insert rows? And there's a bunch of hacky things, but the biggest thing, that was an easy win for our team, being mostly application developers, was to really focus on the indexes. We didn't really get into too many database parameter tunings and unlogged tables and other exotic things, but taking a really hard look at indexes and then queries was a good way to go for our team. So indexes add some maintenance, right? As new rows come in or updates happen, those rows need to be maintained in the index. So there's some overhead there. And there's a bunch of categories of removable indexes besides unused. There's also indexes can be duplicated, and we saw this. I'm not really sure why, but we had indexes, at least one example where the same column was indexed, but the index was duplicated and it just had a different name. I think it was from a migration from a previous tool or something. But so in those cases, they were, once we knew to look for those, it was pretty clear to go through and see if there were any other of those to remove. And then invalid indexes, often we'll build the index concurrently or in the background, and if that fails, the index will still exist, but it will be 0 bytes and be useless. Sometimes that goes unnoticed, and we did have examples of those. So in those cases, the index should be rebuilt. And then redundant indexes too. For example, if you've got a 2-column index indexing A and B, you could use that to query, of course, columns A and B, but also just A. So it may make sense to consider single and multiple column indexes and whether they all need to exist or not. And again, I would also add, this will be most beneficial on the high write tables if you're trying to optimize your write rate, and very large tables. Also, hot updates or heap-only tuple updates require non-indexed columns, and that's an interesting stat to track for your database as well. Those are lower cost updates and are beneficial to increase the number of those. So query statistics. We did enable the PG stat statements extension, and we primarily used the total time and calls, really just kind of a basic usage of it. And the visualization of that data was through this PG Hero tool I mentioned. And by default, it will show you slow queries that are running for longer than 20 milliseconds. That's tunable. And then Postgres' wiki page does have a lot of good monitoring tools at that link. And again, our query optimization process was to use explain when we didn't want to actually run the query, but just get an idea of the execution plan. Explain analyze to look at where the cost portion is most significant within the query execution plan. And the techniques we used were mainly, we were also removing indexes, but if it made sense, we were, of course, adding indexes to queries that were slow. And I recommend focusing on the highest impact queries. PG Hero will show a percentage kind of impact, which is helpful to use your efforts to make the most impact. And then it's also very important, and we developed a separate disconnected database to do performance testing on, but to try to test on as similar to production size of data and size of hardware as possible. Not sure why the screen's doing that. Okay, so PG Hero will show, this is just a quick look again with not a real production database, but it's just showing you in the top row, for example, a query. It will remove some of the specific values, but it will show the average query execution time and the total number of calls. So let's look at a quick query. So this is that rideshare app I mentioned before, sort of like Uber, and it's just going to try to fetch all the drivers and sort them by an average rating and their number of trips they've done. So this is just a quick look at a query execution plan, if in case you haven't seen one before. So reading this from the bottom or the inside portion, reading it up and to the outside, we can see there's a sequential scan on users, and then there's another sequential scan on the trips table. But I have indexes on those, so I'm going to talk about that in a moment as well. Let me get rid of, sorry about that. So some tips for query optimizations. We want to look for index-only scan opportunities. That might be to to query fewer fields. It's really common to do select star in an application and pick all the fields, but if we have 2 columns indexed and we only really need those 2 columns for the application, if we change the application code to just specify those 2 columns, then we'll be able to take advantage of an index-only scan. And another thing that Postgres 11 added was a covering index. So in addition to the fields that you're querying on, you can include additional payload columns as well. That's something I haven't used yet, but would like to try out. And then order by and distinct should raise a little bit of flags. If possible, those add significant cost portions to the query execution. So if it's possible to do those differently, it would be ideal, or to take advantage of the sorting properties of indexes for ordering, or to remove duplicates outside of the query, if possible, in the application. So what if your indexes aren't used? And this comes up both in production and in development. And in production, it's worth investigating a lot of the reasons. There's actually a lot of reasons why they may not be used. But again, Postgres at query execution time is doing a cost-based comparison of different ways to execute the request, execute the query. And it may choose a table scan or a sequential scan when that's more efficient. But I'm kind of bringing this up. And also, I guess, worth mentioning is cardinality, which is the unique values that are part of a column. And then row count, estimated row count and selectivity of that index as well as part of the query execution plan. And really, indexes are best when they select few rows. So in a test database or locally on your laptop, for example, what I did here was I disabled sequential scans because I knew I had indexes on these tables and I wanted to make sure they were being used. So that's that's a little tip that you can take advantage of. So if we look at that, this is again kind of a contrived example, but it was just intended to show that by disabling sequential scans and running that same query I did before, we still have the same number of rows, but we can see now there's an index scan on the users table, and then there's an index scan on the trips table. So let's talk about partial indexes. Partial indexes are kind of double dipping category of both space reduction and performance. Partial indexes avoid indexing common values, and there's a write rate benefit as well. As new rows are inserted, if they don't match the predicate of the partial index, then the maintenance cost is not incurred. Let's look at an example of a partial index. So we've got, let's say we're going to query trips with no rating, and in our Uber-like ride-sharing system, almost all the trips have ratings because we want trips to have ratings as part of the system. So we have a minority or a few rows that don't have a rating. So I just made up some numbers here, but let's say we had 3,000 trips and 750 without a rating. These kinds of scenarios are indicators that a partial index might be useful. So we can see that the query execution plan estimated 750 rows, but there's an index condition. So in addition to that index, it's going to then scan through that index and just get the rows where the rating is null. So the idea with partial indexes is to bake that where rating is null portion into the index creation itself. So now I've replaced that index with an index in that first line where rating is null. And we can see it's still the same 750 estimated rows, but we no longer see that extra filter line. It's gone. And then we can see that the partial index is about 60% smaller. And if you have indexes that are hundreds of gigabytes, it's pretty nice to shrink them down, and they're going to be, there's going to be performance benefits as well. So our results were we did create some replacement partial indexes for several existing indexes, and one of the biggest reductions was actually 97% smaller. So it served the same purpose for the application, but it was essentially almost free, right? It was 97% smaller in size, and yeah, in large tables it's significant. Reducing columns on multi-column indexes. I think a lot of times columns are added and they're not actually needed as part of the query execution plan. Postgres can actually combine multiple single column indexes as part of its query execution. So sometimes they're not needed to index all of them. The exception would be if you are trying to do an index only, trying to do a kind of a covering index that covers all the fields that you need. Also take a look at the ordering of the columns in the index. So we were able to fix more than 10 queries that were identified, which was great. PG Mustard actually is a sponsor of this conference as well, but Michael from PG Mustard is a great guy, and this is a cool query visualization tool that I came across, PG Mustard. So the query execution plan there's a lot of information in there, but being able to take that information, export it, and then get some recommendations and tips about those different nodes in the plan is quite valuable. And I've also been working my way through this book, PostgreSQL Query Optimization. It's pretty new, and it's a great book. I recommend it. Postgres has on their wiki page a bunch of additional performance analysis tools. The previous presenter went into a lot of detail with PG Monitor, but I wanted to call that out because it's relatively new as well, and it's an extension for 11, 12, or 13. And then PG Analyze has a free tool called Index Advisor, which will also give you recommendations for index opportunities for your database as well. So that wraps up performance. Last section is errors. Wrapping up here shortly. Thanks for coming to my talk prior to lunch. I appreciate it. I'm sure everyone's a little bit hungry. So query errors, there's a lot of different errors that we've observed and that can happen as part of queries executing in a real system. Queries sometimes never finish. Sometimes checking out a connection from the pool never finishes. Sometimes trying to acquire a lock never finishes. Transaction might be open and never commit or roll back. So these are all some things. This is not a comprehensive list, but these are some real world things that we've observed. So what are we going to do? We're going to add some timeouts. So we're going to add a statement timeout. This is probably one of the most valuable ones for a running app. And we're just going to say if the query is running for more than, in our case, we had it set to just 5 seconds, we would just cancel it. And that would allow us to preserve the overall system resiliency and integrity. And those typically represented an erroneous query, as the queries should generally execute in much less time, more in the order of milliseconds or to 100 milliseconds. Checkout timeout. This is a timeout to set to add as a safeguard for connections that are never able to be checked out from the pool. Lock timeout is something that can be set on the client side as well. And again, a maximum amount of time to wait to acquire a lock. And then idle transactions. These, interestingly, we can set these with our active record connection pooler and then also on the server with the idle and transaction session timeout parameter as well. And again, the idea here is to guard against these scenarios. So last error class was replication errors. We did use replication, and replication could sometimes get so high that replication could stop, which is very disruptive if you're expecting a lot of queries to run on the replica. So replication lag is something worth monitoring if you're not already. And in certain less common scenarios, replication can actually conflict with vacuum that's running on the primary. This link has some more details about that. So those are the 4 categories: connections, space, performance, and errors I wanted to cover as kind of how we scaled up and operated Postgres. I do have 2 summary slides, and that'll be it. Before I do that, special recognition. My past team for opportunities to really learn Postgres on the fly and apply a lot of these techniques. Special thanks to David R. For helping out a lot. And then some folks that listened to a practice run of this talk. And then the Postgres community, including not only, of course, committers and contributors to Postgres, but folks writing documentation and blog posts. There's also a Slack group if you're not aware of this group. It's easy to sign up for if you're using Slack at work already. You can pop it open, and I'm in there as well. So 2 wrap-up slides, connections and space summary. So we added a connection pooler to increase our performance and enable additional scale. We recreated 30 indexes to eliminate the bloat, and that would be something that could be done periodically. We just did it as a one-time task. We removed more than 100 unused indexes that were not serving a purpose for the application. We distributed the write load by relocating the metrics tables that I was mentioning before. We also distributed the read load as much as we could by moving more queries to the read replica. We also tuned auto vacuum to run more frequently and run for longer when it did run. On the performance and errors side, we added a dashboard to show our slow queries and focused on the top 10 and tried to improve the execution time of those. We created awareness on the team of the cost of indexes and tried to kind of tamp down the rate that they were introduced a little bit. We moved more than 10 queries to the replica, and then we also added a bunch of timeouts related to different error states, queries, database connections, and locks to create more resiliency in our system for queries that were erroneous. So we made Postgres fitter, happier, and more productive. And that's all I've got for you. Again, the slide is available, or the deck is available here. And thanks again for all of your attention and time today.
Good time for a couple of questions if there are any.
Just a quick question about the zero downtime migration of, the analytics-oriented data elsewhere. I don't know if there's some constraints on, or I'm not super familiar with extension constraints or such with RDS, but did you look into like logical replication for that?
Yeah, we weren't currently using logical replication. We looked at it more in the context of replacing our ETL system that would pull data from different app databases, and then we used Redshift as an analytical database, also built on Postgres, I think. But we didn't have any existing running logical replication, but that would have been a great way to do it too. That makes a lot of sense to me, to be able to transform those rows at the time that they're created and send them over to another replica. But yeah, we didn't use that in our case.
Anyone else? All right, well, thank you.
All right, thank you.